we could have done this early this course and then complex analysis, but that's fine. It's kind of a revision as well. Um,
That's right.
yeah,
Actually, we could have done a topology course beforehand, and we didn't have to do all those things. Yeah.
yeah,
Uh, I did that course because I thought I should read a bit about it. So anyway,
right,
good.
right. No, but it's this is actually good the way we are going. Uh, I mean, one thing that I was thinking for later, it may be not applicable. Um, we need to see how this is applied in some physical problems. I wanted to see, like a uh, in like geometry problems, for example, right? Is there applications? How that is? How probably that might be a different course. I don't know what it is called. Like um, it is part of metric spaces, right? It's like
Yes, there should be many applications. It will not be a problem to see some. Right now, we are at a elementary stage, but
right,
mm. Everywhere you need to use a lot of things. For example, you are doing some optimization problems. Okay? I mean, topology is not directly used there, but it is
right,
indirectly everywhere there. Suppose you're looking some kind of optimization problems. You want to maybe have a surface satisfying certain regularity. In an automobile engineer requires the surface to look like that. So you want to optimize some surface area or something. So what you do, you take a huge class, and in that you take a whole lot of indirect methods. You take a whole lot of functions and sort of minimize the area functional on that big space. And when you minimize, you end up with some minimizing solution for guaranteed resolution or not. But what is the space in which you are talking about the optimization? That space has to have a topological structure in order to say some sequence is converging to something, isn't it? In that sense, we have to have topology everywhere, right? You use it all the time, even if you don't say directly. Eh?
right,
Uh, Indirect methods mostly people take in a very general setup. They look at Sobolev spaces, some kind of a very interesting, normal linear spaces. And in that you do the minimization process or maximization process, whichever is your interest. And that process itself requires a proper topological space. So there is that one example. And what is the algebraic topology gives you a whole lot of handle and very interesting things. There will be fixed point theorems also are there in topology. Fixed point theorems, we don't do anything at all in our course, but maybe beyond the course, I will slightly explain a few things. Uh, for example, if you look at a vector flow on the surface of the earth, okay, there is absolutely no way you can have a smooth vector flow without it vanishing at some place. That means if you comb your hair, however way you comb the hair on the top of a hairy ball, you will not escape a place where you found that the flow widens and you get a 0 point, which is called cowlick. When we do this little place you see on the top of the head is called cowlick. Okay, for one reason, that's the word in English. Cowlick. You cannot comb hair on the top of a sphere without having a cowlick. Whereas if the space is of the shape of a torus, then you can always move it very, very well and without having any cowlicks. So the topological structure of the space put some inhibitions on the solutions of differential equations. A vector flow is like a differential equation uh, giving you the vector flow at the surface. So the solutions to the differential equations on various different surfaces have some uh, deep connection to the topology. The topology will tell you whether you have solutions or not. Okay, so in a sense, topology for me is like more an underlying thing. It has to be there everywhere. You need to use it. Practical applications, yes. For example, I want to prove this Cowlick theorem. are fixed point theorem. You know, fixed point theorems apparently is quite. I don't know really much about them. Apparently, quite useful in solving a lot of uh, practical problems, differential equations, and things like that. Some practical problems are solved using fixed point theorems. I'm off hand saying anything. Don't take it from me. Okay, roughly because I'm not expert in that. Topology will be there everywhere. Okay.
Yeah.
I will try to give you some examples.
Right.
Okay. All right. I think Kiran
Yeah.
Kumar is also okay. Yeah.
Yes. Yes.
Welcome
Yes,
to.
sir. Good morning.
So we will just continue our lecture. What we did is very nice. We understood what compactness is now. In the case of a metric space, compactness is equivalent to sequential compactness, right? Actually, compactness, the word literally the compactness, it's a handleable. You can handle it. Is something not so easy to feel at the first sight in general abstract topological spaces. But slowly you will get a grip of it and you understand what compactness means. Now, if every open core set admits a fine subcover, is really a very stringent condition on the topological space, which is compact. Topological space is within your hands. You can handle it unless it's spread over to infinity in all directions. Okay. So in the matrix space scenario, we even learned very nice. We showed eventually compact spaces are sequentially compact, and sequential compact spaces have Bolzano-Weierstrass property in the sense that every infinite set has to have a limit point in it. And we proved something more than that. I said they are totally bounded. Compact matrix spaces are totally bounded. We proved that. Totally bounded means what? You can have a epsilon net of the space for every positive epsilon greater than zero. If anybody gives an epsilon greater than zero, I will be able to find finitely many points in the topological space so that every point of the topological space is within epsilon distance from one or other of these finitely many points. That's what you totally boundedness. So yeah, the whole space is within your hands. I have a net in epsilon net. What is this epsilon net? Eh? What is this epsilon net? Every point in the space has to be very close to these finitely many points of the epsilon net, so close that the distance is less than epsilon. And it should happen for every epsilon greater than zero. That's what total boundedness means. Every sequential compact metric space is totally bounded. Okay. Towards the end of the whole story yesterday, I said something incorrect. Okay. Which is, I said totally bounded spaces are sequentially compact too. It is not. Totally boundedness and completeness must be added in order to say, in order to have compactness. That's what I would like to prove today, that a topological space is compact if and only if it is complete and totally bounded. Sequentially compact spaces are totally bounded, but not complete. But its completeness is also added. Other way around is also is there. So what is that we proved so far? So far, we proved that in a metric space, the following are equivalent. In a metric space, X may be D, the following are equivalent. Uh, so what are they? Uh, Sequential compactness, X is compact, B, X is sequentially compact, and C, uh, X has the Bolzano-Weierstrass property. All these three things are equivalent. I also have showed you that sequentially compact implies X is sequentially compact implies X is totally bounded. What does totally bounded means? That is for this one. That is, for every epsilon greater than 0, x admits in epsilon net, x admits an epsilon net. What do you mean? That is, there exists a finite subset, say A of x, okay, such that for each x in x, there is an A in A such that the distance of x from A is less than epsilon. Compactness means so solid. Okay, is it clear now? Everybody understand what I mean by compactness? We get a feel of what compactness is with this theory. Okay, this is what we discussed. Now I'm going to prove a small result. Uh, if I remember, while doing complex analysis course, I started it and I was not able to complete it. Okay, I think we left it there. But you see the proof here once, which is the following. Um, if I have a compact metric space to another metric space y, if I have a function which is continuous, then that function has to be uniformly continuous. So what do you mean by a function is uniformly continuous? Let x d1 y d2 be metric spaces. A function f from x to y. You know what continuity means? Inverse image of an open set is open set, right? Which can easily be proved equivalently in terms of metric space also. See, if x y to x to y is continuous means what? Continuous means continuous at every point. So continuous at every point means say f is continuous at each x in x. Okay, what do you mean continuous at x equal to x means for every epsilon greater than 0, there exists a delta greater than 0 such that distance between y and x, y is in this, okay? Oh, y is in x, and distance between y and x is less than delta, implies distance. This is the distance in the first one, distance in the second one between fx and fy is less than epsilon. That's what continuity at the point x means. Okay. If y is very close to x, fy should be close to x. You can make fy as close to x as you want. For every epsilon greater than 0, there's a delta greater than 0. Such that whenever I take objects which are that much close to x, that means delta closer than delta close, less than delta close to x, then fy will be epsilon close to less than epsilon close to fx. That's what continuity at x means. And continuous on the topological space means is continuous at each point of x. Now I have talked about the inverse uniform continuous. Okay, f x to y. Maybe I'll do that first. Is said to be continuous. If it is continuous at every point of that, no need. I said what continuity is. Okay, is said to be uniformly continuous. Okay, if this continuity, this choice of delta corresponding to epsilon depends on where I'm talking about continuity. So this delta actually depends on x. Delta will depend on x. Various different x's will have very different deltas, and there may not be a minimum delta positive. So that's what the trouble with this is. But uniform continuity means same delta works for everything. if for every epsilon greater than 0, there exists a delta greater than 0, such that, okay, for x comma y in x, distance 1 between x and y is less than delta, implies distance in 2 of fx and fy is less than epsilon. So this choice of delta will not depend on x. In general, for all x and y in x, if x and y are too close to each other, then fx and fy also should be good. That's what uniformly continuous means. I hope you understand the definition. It is a theorem. Let x rho comma y be metric spaces. D1 and D2 are there. X comma y be metric spaces and X compact. Then any function x to y that is continuous is also uniformly continuous. Any function f x to y that is continuous, any continuous function f x to y is any continuous function f from x to y, f from x to y is uniformly continuous from x to y. Any continuous function from x to y is uniformly continuous. Okay, sir? Okay, the proof is very easy. Actually, I should have recorded this also. I also proved that if X is compact, then the theorem I proved, I think I proved that if X is compact, every open cover of X will have a Lebesgue number. I proved it for sequentially compactness. Okay, fine. If X is anyway compact and sequentially compact is the same. If X is sequentially compact, every open cover of X has a Lebesgue number. We proved this also. Okay. What do you mean has a Lebesgue number? It means that open cover I have chosen for this compact metric space has lots of open sets. There are big open sets, small open sets, and so on. But I have a Lebesgue number A greater than 0 means every subset of X whose diameter is less than or equal to A must be in something or other of the members of the open cover. Remember that? Okay, sir. So in order to prove this, first I say this, let, I want to prove it's uniformly continuous, right? So take any epsilon greater than 0. Let epsilon be greater than 0. Okay. If you look at for each y in y, maybe I can even say for each x in x also. For each x in x, where is f of x? F of x is in y. Okay. So the ball of radius epsilon by 2 centered at f of x is an open set in y. Okay. And so this inverse image, because f is continuous, its inverse image is also open. Okay. Hence, f inverse b epsilon by 2 fx is an open set in x. And small x is in this. So if you really look at f inverse b epsilon by 2 fx, where x is in x, is a open cover of x. Okay, is an open cover of x. What does it mean? Uh, then it admits a finite subcover. Okay, it admits a finite subcover. Hmm? Yeah, is that right? Maybe I don't even need to do that. Okay, is an open cover of x. But uh, this open cover will have a Lebesgue number. Okay, since x is sequentially compact, then sequentially compact. Since x is uh, compact, it is sequentially compact. And so it has and this cover has to have a Lebesgue number. And so G has to have a Lebesgue number, say delta positive. Okay, it has a positive Lebesgue number. What do you mean by that? So therefore, okay, for all x comma y in x, okay, the set containing x comma y for all x and y. Let me go to the next page. It's very simple. Done anyway. Uh, let x comma y belong to x, and distance between x and y is less than delta. Then the diameter of the set consisting of x comma y is less than delta. Okay, and therefore this set has to be in one of the members of the cover. Okay, hence there exists. It has to be one of the members of the cover. You go back and you see that the open cover is this. Okay, of the compact space. So that x and y belong to one particular such thing. So what is that? There exists a maybe x naught in x such that x and y both belong to f inverse ball of radius epsilon by 2 centered at x naught. Okay, is that right? So therefore f of x comma f of y, x and y are in this. Therefore f of x comma f of y are therefore in B epsilon by 2 x naught. And that means the distance between fx and fy, sorry, f of x naught. Okay, this is the ball in the right hand side, right? So a distance between them is less than equal to distance between f of x and f of x naught plus distance between f of x naught and f of y. But each is less than epsilon by 2, less than epsilon by 2. So less than epsilon by 2 plus epsilon by 2 is equal to epsilon. So we finished. So if distance between x and y is less than delta, distance between fx and fy is less than epsilon. For every epsilon greater than 0, I'm able to choose the delta doing that. Therefore, f is uniformly continuous. This completes. Okay, right, sir? What do you say? Now, I want to prove that a topological space is compact if and only if it is totally bounded and complete, a metric space. So here is the theorem. A metric space X is compact if and only if it is complete and totally bounded. Okay, maybe I just said what complete means. I did not pay attention. I should have introduced that in this course too. We have used the completeness so many times in complex analysis. So a complete means what? A metric space is said to be complete if every Cauchy sequence in it converges. That's what complete means. Okay. What is the definition of completeness? Okay. Uh, a metric space X is said to be complete if every Cauchy sequence in X has a convergence of has every Cauchy sequence in X is convergent. Is convergent. Cauchy sequences need not converge, but in a complete metric space, they converge. Okay. If completeness and total boundedness are there, then I get compactness. Of course, other way around is easy. Compactness implies completeness and totally boundedness is easy. Already proved compactness implies totally boundedness. And additional compactness implies completeness. That's also not a very completeness means what? Every Cauchy sequence converges. Then it's very easy also to see that if a Cauchy sequence has a convergent subsequence, the Cauchy sequence itself will converge. So if I take a Cauchy, if I take a compact metric space and take a Cauchy sequence, that's an infinite set. Plus it's repeating again. If it's repeating again, uh, there is a convergence subsequence. If it's infinite, then I have a convergence subsequence. Oh, then I have, because it's compact, okay, that infinite set has to have a limit point. And so a convergence subsequence, but Cauchy sequence has a convergence subsequence space, whole sequence itself converges. So here is a little lemma. Okay, if a sequence is Cauchy and has a convergence subsequence, then sequence itself will converge. If a if a so I have to define all these things maybe once very quickly. Why not? Let me define all them for you. Just what is the completeness? Why not? Let's make it okay. Uh, Definition of completeness. A a metric space X is said to be complete if every Cauchy sequence every Cauchy sequence in X converges. You know what a Cauchy sequence is? Xn in X is said to be Cauchy, said to be a Cauchy sequence. Okay, if for every epsilon greater than 0, there exists a n naught, a positive integer, such that distance between xn and xm is less than epsilon for all n and m greater than or equal to n naught. Okay. So the sequence, our interpreter says, the terms of the sequence are coming close to each other, right? That's what is Cauchy. And here is a little lemma. If yes, a Cauchy sequence which has a convergence subsequence must converge. A Cauchy sequence which has a convergence subsequence which has a convergent subsequence has to converge. Converges. Okay. So now the theorem I'm trying to prove. Okay, the theorem I'm trying to prove is that a topological space is compact if and only, sorry, a metric space is compact if and only if it is complete and totally bounded. A metric space is compact if and only if it is complete and totally bounded. Okay, here's a proof. One side becomes too easy for us, Compact metric space is already proved. Compact metric space is totally bounded. Compact metric space is sequentially compact and it's totally bounded. I only have to show that compact metric space is complete. Well, if I take a compact metric space, every infinite set in it has a limit point. So if you take a Cauchy sequence in it, that's an infinite set. Unless it's the same thing is repeating, then already I have subsequence which is converging. Otherwise, if it's an infinite set genuinely, it has a limit point. It has a limit point means there is a subsequence of the Cauchy sequence which converges to that limit point. But in a Cauchy sequence, if there is a convergent subsequence, the Cauchy sequence itself converges. Thus, every Cauchy sequence converges, and therefore the space is complete. So one side is obvious. Okay. So it is easy to see that compactness implies completeness. Okay. Well, totally boundedness we proved anyway. We already proved compact implies totally bounded. Okay, X is compact implies X is totally bounded. So I have to prove the other way around. Okay, that is complete and totally bounded implies the space is compact. That is what I'm going to prove. Okay, we shall now show we shall now show that X is complete and totally bounded. Complete and totally bounded implies that it is compact. Implies that it is compact. Okay, very good. So assume X is complete and totally bounded. Okay, assume X is complete and totally bounded. I want to show it's compact, right? That means so many ways I can show that it's compact. Uh, I have to show that every open cover admits a finite cover, finite subcover, right? Oh, yeah, otherwise I can show you sequentially compact. Okay, sequential compactness and base compactness. So sequentially compact means I have to show that every sequence has a convergent subsequence. That finishes the problem. Okay, so we'll do this by showing X is uh, we'll show we will show that X is sequentially compact. then it becomes compact. Sequentially compact means I have to show that every sequence converges. So I take a sequence. In order to show it converges, I will extract a subsequence of this sequence, which is Cauchy. And since space is complete, the Cauchy sequence converges. That means the subsequence of the given sequence converges. Okay? Take a sequence. Let S1 contain X11, X12, or X21, etc. I can show X12, X13, etc. be a sequence in X. I could have taken X1, X2, etc. as a sequence. For some reason, I'm having an introducing a notation. What I'm going to do is I'll start with a sequence. I produce a subsequence. I produce a subsequence. I so on. Produce a subsequence. Amongst these subsequences, I take some elements. Some kind of diagonal process will be used. So because of that, the first sequence that is given to me, I have assumed the sequence is X11, X12, X13, etc. Suppose this is a sequence in X. I have to show that it has a convergent subsequence. Actually, I prove that it has a convergent subsequence by showing that it has a subsequence which is Cauchy. Completeness guarantees the convergence of that sequence. Okay, I have to extract a Cauchy a subsequence of S1, which is a Cauchy sequence. Okay, let X1, X12, X13, etc. be a sequence in X. X being sequentially compact, it is totally bounded. Okay, and so it can allow in a 1/2 net, since X X is not compact. X is not compact. Compact is what I want to prove. Since X is totally bounded, since X is totally bounded, yeah, I mean that bounded, it has a 1/2 net. Okay, that means what? I have a finite set, maybe some y1, y2, etc. yn. I have a finite set A, so that every member of X is within a 1/2 distance of some member of A. Okay. In other words, if you look at half neighborhood, balls around each yk and take the k equal to 1 to n, you are saying that this is the entire space X. So finitely many balls are covering the capital X. Okay, and these are infinitely many in X. So I think infinitely many of them should be in one of the balls, unless of course it itself has one element repeating infinitely many elements. If any element repeats infinitely many times, that's already a convergence of sequence. If I don't have, then I get infinitely many of them will lie in X, but that is union of finitely many. So infinitely many of them should lie in one of the balls. So there exists a subsequence. I call that S2, consisting of X21, X22, X23, etc. of S1, which will all be within a half ball. Okay, S1, so that they all lie within some half ball. Okay, within some half ball, they all lie so that they all lie in a ball B half centered at some point. I can call that some X2. Okay, but I can have another 1/3 net. That is this one another subsequence. Okay, so again, It's totally bounded, right? And for every epsilon gas engine, I had epsilon net. So there is a 1 by 3 net. Again, uh, again, uh, X has a 1 by 3 net. So this X is going to be a union of finitely many balls centered at some arbitrary points, maybe Z1, Z2. Where too many names are there. Why I use the same YK, K equal to 1 to N, some other YK. A ball centered it, and maybe more of them, maybe some M, doesn't matter. And these infinite many things should lie in this finite union, and therefore some subsequence will lie in one of them. Okay, so there exists a subsequence, okay, S3 consisting of X31, X32, X33, etc. of S2, so that they all lie in a ball B1 by 3, centered at some other point X3, and so on. So these points are all in B half X2. That means between distance between any pair of them is no more than 1, whereas distance between any pair of them is no more than 2/3, and so on. Okay. Now let us look at the subsequence S consisting of X11, first element of the first sequence, and second element X22 of the second subsequence, and X33 of the third subsequence, and so on. So what happened? Another subsequence says all of them will lie in particular ball like them of radius very small 1 by n. So you can see that this is very easy to see that this is a Cauchy sequence. Cauchy subsequence of S1. Is that okay? Right. For example, after n, xn n, x n plus 1, n plus 1, etc. They all lie in this ball B 1 by n xn. So x n n, x n plus 1, n plus 1, and so on. They all lie in that. That means distance between any two of them is less than 1 by n. So the distance between pairs of them are becoming smaller and smaller. Okay, so indeed xnn and some xmm, the distance between them is less than 1 by n. As n gets bigger and bigger, I can see that these things are coming closer, and that's a Cauchy sequence. It's a Cauchy sequence, subsequence of S1. But Cauchy sequences in the space converge because that's complete metric space. Since X is complete, yes, converges. The sequences converges. Okay, so I started with a sequence. I have a convergence subsequence, and so the space is sequentially compact. Okay, and thus every sequence in X has a convergence subset. Yeah, and that's what I promised. I promised that I'll prove that X is sequentially compact, which implies X is compact. Done. Okay. So this is what it is in a metric space. Compactness is equivalent to completeness and total bondedness. Compactness implies completeness also, not the other way around. I can create a lot of examples. Completeness uh, need not imply compactness unless we have total bondedness. We should be able to create examples. Okay. Any questions so far? Okay with this? As a corollary, very simple thing. If I am going to take a closed subspace of a complete metric space, a complete metric space, closed subset of a complete metric space is closed. Such a closed subset of a complete metric space will be compact if and only if it is totally bounded. A closed subspace of a complete metric space, complete metric space is compact if and only if it is totally bounded. Obvious. If we take a closed subspace of a complete metric space, then that subspace is complete. Why? If I take a Cauchy sequence in the closed subspace, it is Cauchy sequence in the big space, and here it converges, and the limit, because the subspace in which I have taken the sequence is closed, that limit has to be in the subspace. So this sequence converges, this Cauchy sequence converges to the subspace. The subspace is complete. Here is Y is a closed subspace of X. Closed means what? Every sequence in it converges, it has to converge inside V. The limit will not go out. Now, so if I take a Cauchy sequence here, there is Cauchy sequence here. Here it converges, but that limit point is the limit point of a sequence inside this. Better be in this because Y is closed. That means that subsequence actually converges in that. So a closed subspace of a complete metric space is complete. So if I take a closed subspace, if it is a complete metric space, then, and if it is also totally bounded, then it is compact. So there's nothing to prove. That's why it's just probability. Okay, I think we have done a good job. Now I will talk about a little bit about function spaces. Is discussing some of the properties, some of the function spaces, metric spaces, and we want to talk about other things. To that end, suddenly I don't want to go out. He has talked about Banach spaces and all. We don't want to go too far off right now in topology, but bare minimum I think I have to talk about. Okay, you have what are called linear structures in algebra. A vector space, for example, is a linear space. Vector space is one in which you have the one operation addition with respect to which any two elements in that space are added, and that is in the space itself. Associative law, existence of additive identity, and existence of additive inverse, and also commutativity. These things will ensure something is a right an abelian group, and there is an external multiplication also, which gives you. So let's see that. Okay, here is the definition of a linear. I don't want to do all these things, but maybe just a little bit. Linear spaces. We'll take up a course in linear algebra altogether, then we can do it. Or maybe we take up a course in functional analysis. There we also do that. A linear spaces. What is that? Uh, a set. Here is a set L together with a binary operation addition and an external operation dot is there. Okay. This right. L, let L be a non-empty set with a binary operation plus on it uh, and an external multiplication. Maybe I should write in some uh, that is for each alpha in R or C, and X in L, you have alpha X we have alpha x in L. Okay, I have these two operations on L that satisfy. I think you guys know these things very well. That satisfy. First is okay. So what is that? Binary operations. So for each x and y in L, for each x and y in L, x plus y is in L. That's what you mean by binary operation. This should be commutative. X plus y equal to y plus x for all x and y in L. There is an associative law. X plus y plus z is equal to x plus y plus z for all x, y, and z in L. Existence of additive identity. There exists a special element 0. Okay, in L. Okay, such that x plus 0 equal to 0 plus x is equal to x for all x in L. Okay, and additive inverse for each x in L, there is another element, I can call it minus x dashed in L, such that x plus x dashed equal to x dash plus x is that special 0. Actually, if there is a 0, it's very easy to show that such 0 is unique. Such element 0 will be unique. You won't have more than one. Okay, you don't insist on the uniqueness, you actually prove uniqueness. For each x, there is an x dash, that's x plus x dash equal to x dash plus x equal to that unique 0. And the x dash is called the additive inverse of x. X dash is called additive inverse of x and is denoted by minus 1 or minus x. Okay, so I want these properties to be satisfied, and the external property that is there should also satisfy this condition. Alpha plus beta x is alpha x plus beta x. Okay, and alpha into x plus y is alpha x plus alpha y. Alpha into beta x is same as alpha beta into x. And finally, 1 is there in R, right? 1x is x for all x in L. For all alpha beta in R or C. Okay, a linear space underlying field can be R or C. So for all alpha beta in R, let's look at real ones or complex ones. Right? For all alpha beta in R and x in L. This is for all alpha in R and x in C. I could probably have alpha to be in complex. So it's a L is a linear space over the field of complex numbers, or L is a linear space over the field of real numbers. Okay. We will very easily see that let X be any non-empty set. Let X be a non-empty set. And L, suppose I take all functions defined in X, F, such that F is a function X to R. It can be to C also. If it has to be in C, that's another story. You look at all the real value functions defined under L. You can easily see that L has some simple properties. If I add two functions, is meaningful, etc., etc. So L with addition of functions, what is that for f comma g in L? F plus g is that another function? What is f plus g of x? F plus g of x is fx plus gx. They are in R for each x in x. So that defines f plus g. Okay, and multiple alpha f at x is alpha into fx for all x in x. So these two operations will make L is a linear space over R, or it can be over C also. Okay, L is a linear space, and in particular, I look at all the members of L which are bounded. F is bounded. Bounded means what? That is, there exists a m greater than 0, such that mod fx is less than or equal to m for all x in x. I can take bounded functions. I can take all functions, not a problem. I can take only bounded functions, whichever it is. Okay. First of all functions, I already said, is a linear structure. I can add two functions. Eventually I want to do better than that. I don't want to take all functions. I want to take, in case X is just a subset, right? In case X is a topological space or a metric space, then I would look for not all functions, but only continuous functions, maybe bounded continuous functions. And we will study those function spaces in our course. In general, I can have all functions that will be a linear space over that. In particular, suppose I have, one second. Excuse me. In particular, okay, I look at all f uh, which are functions from x to r and that are bounded. F is bounded. Okay, then that is what there exists a m greater than 0 such that mod fx is less than or equal to m. Okay, for all x in x. You can actually introduce you can make this B not only a linear, it's not only a linear space, you can also introduce a norm on it, normed linear space. Okay, so what is a normal linear space? On a linear space, okay, I have okay, normal linear space. Just a digression from what we are doing, very quickly writing down a few things. A normal linear space, what is that? Suppose I have a linear space. Let L be a linear space. Okay. If for each x in x, we associate, if we associate, if we associate to each x in x a real number, norm x, okay, satisfying the properties, couple of properties. Norm is always non-negative, okay, for all x in linear space L, okay. And actually, I will assume that norm is 0 if and only if x itself is 0, there is null space, right? And equality holds if and only if x is the 0 element of L, norm x plus y is less than or equal to norm x plus norm y for all x and y in x. Okay, and norm alpha x is mod alpha norm x for all alpha in the underlying field R and x in X. If these properties are satisfied, I call that a norm. Is that what it is? All right. These are the properties a norm is supposed to satisfy, right? If I have a norm, I can easily create a metric, and so on the normal linear space, I can easily, okay, if L is a normal linear space, uh, this is the norm on L. We can introduce a metric on L easily. We can introduce a metric on L. You just have to say distance between x and y is norm x minus y for each x and y in L. You can see that D becomes a metric. Okay, D is a metric on L. So L becomes a metric space. Are you following? For example, on the space B I just introduced, which is space of all functions from this abstract set, doesn't have any topology on it, to R is bounded. Okay, then for any such F, you introduce norm F to be the supremum of mod fx. Supremum exists because F is bounded. A bounded real number, right? If you look at all the bounded real number, there is a supremum for that. So this supremum exists. So you will see that this makes B a normal linear space. This makes B a normal linear space. Are you following the discussion, right? Now, in case X is a topology, I'm not going to study the normal linear spaces and linear spaces. Actually, later on, we'll study a course in function analysis. In function analysis, I have a linear structure and there is a topology. They actually interact each other in a decent way. You have normal linear spaces with, right, with some topology also. Of course, topology comes already if you have a norm, there's a metric coming, therefore it becomes a topological space too. So study the linear structure together with the continuity that you get from topology. That is what we do in function analysis. Okay. This makes B a normal linear space. Okay. For example, I have taken in general, suppose I take a topological space. X is not just any set. Let X be a topological space. It can be just metric space also. Let X be a topological space. And C X R consists of all functions which are continuous on X, continuous and bounded also. Okay, CXR is all functions which are continuous and bounded. Yeah, I think that's what is notation is. So we'll go with that notation. Space of all bounded continuous functions. CXR is the space of all functions F X to R, which is F is continuous and bounded. F is bounded and continuous. CXR becomes a sort of a normal linear space. Okay, it's a linear over R. CXR it is a normed linear space. It has a metric structure. The norm is the following. Norm of f, it is continuous and bounded. So this is the supremum mod fx, x in the domain capital X. It's a topological space. Continuity also makes sense because X is a topological space. If it's only abstract set, continuity doesn't come into the picture. We're not studying everything. We're studying only actually these function spaces is what I study. I could have C X C. See in this norm, you have for each alpha in R. Okay, you can talk about alpha F norm. You're multiplying with a real number because fx is a real number. Multiplication with a real number makes sense. But if fx is a complex number, I can multiply with complex number too. In that sense. So what is C X C, the complex plane? If you use that, that is a set of all functions from X to C. C also is a topological space. X is a topological space, so it makes sense to talk about continuity. F is bounded and continuous. So in this case, for each complex number Z, I can talk about ZF. Okay. So this is a linear space over C. That's a linear space over R. Okay. It is a normal linear space over R. So underlying field is R. For this underlying field is C. It is a normal linear space over C. Again, because the norm is there, metric is coming, and therefore there is a topology. And so within the topology, I can talk about convergences of sequence of functions. We can discuss those things. Okay. Now, okay, I think this I will take it up later on. We have just introduced basically what it is. I think that's what we actually. I'm doing all these things eventually to introduce what is actually Arjuna theorem. Okay, we have not proven that when we did, what is that complex analysis, especially Ascali-Arjuna theorem says about the space. If the space has certain property, something like equicontinuity or something, this becomes compact. Compactness, is very much useful. Compactness implies sequential compactness. So I want to know when this space is compact, okay, or sequentially compact. It happens if it satisfies a couple of conditions, okay. So Ascali says the space CXR X is compact if only it is bounded and equicontinuous. So there is a notion of equicontinuity. Equicontinuity means all functions in the space together are continuous. That is, for an epsilon, there is a delta that we create will not depend on it. So, okay, right. A family F of subset of C X R or C X C, okay, is said to be equicontinuous. If what? If for every epsilon greater than 0, there exists a delta greater than 0 such that, okay, there is a metric here, right? The metric is coming from here. DFG equal to norm F minus G. Remember that? Such that also equicontinuous if, oh, I see. Maybe I should allow X to be a metric space to talk about this. X should be a metric space. Okay. X should be a metric space here. Let X be a metric space. Okay. F is a family contained in either a CXR or CXC is said to be equicontinuous if for every epsilon greater than 0, each function is continuous, right? What I want is all functions together should be continuous and epsilon and delta should not depend on the f. If for every epsilon greater than 0, there exists a delta greater than 0 such that distance between x and y is less than delta implies distance between, that is modulus. On the right hand side, RRC, right? Modulus of fx minus fy is less than epsilon for all f in the family f. Okay? Family of functions from x to r is said to be equicontinuous when every member of the family is actually uniformly continuous, but it is uniformly on f. I hope you understood this. And I'm going to get a condition for the compactness of such a family. That means such a family of functions are taken CXR. I want to talk about convergence of such a family. And this family may be a sequence in CXR. And I want to know whether this family converges. What is the meaning of convergence in this topological space? These are the things we want to explore. We'll prove to you that in case such a family is bounded as well as equicontinuous, then that will be compact subset of that, is what I will prove. Okay, we'll stop the discussion here. Okay, I want to, so as far as Argela's theorem is what I would like to prove next time. So I don't want to say too much about function spaces, that is why I just jump through everything. That's a different topic. We'll study, actually, studying functionals is one. Okay, we'll do that thing. Sir, any of your comments or questions? Okay.
Yeah, I think it's good. I have to go through this one more time, but I'm okay now.
Okay. Yeah, I didn't do much. I just defined a few spaces and so on. Just look at those things, nothing much. And we are also not going too far about normal linear. Actual function analysis is the study of all these normal linear spaces, Banach spaces. Banach spaces are actually normal linear spaces together with some completeness action. Then Hilbert spaces, where norm is there, instead of, yeah. Yeah, Hilbert spaces. We study of all these things. Here, Kumar probably does, and then I'm sure people saying quantum mechanics will study Hilbert spaces. So,
Yes,
okay, sir, we'll stop here. What happens is Hilbert spaces, you also have an inner product. Dot product is there. So the norm will come from the dot product in Hilbert space. In general, in Banach spaces, you have no need of inner product. So, and normal linear space is inner product is Hilbert space. Here is just normal linear space with completeness is a Banach space. We study Banach spaces, Hilbert spaces, and operators and those things in function analysis. It's fun to do the function analysis. There's another place where you need to have a lot of topology. Okay, sir.
Yeah.
That's it.
thank you, sir.
Thank you.
You guys have a good day.